Okay, so we are going to start our next unit, and this is going to be Kinetics and Equilibrium. And we are on page number 134 in your blue notes book. Okay, so I'm going to switch to tablet mode, and you're going to get yourselves ready. And you should have your reference tables, of course, for this lesson as well. All right, so on page 134, let's begin. All right, as with all of our notes, we have vocabulary related to the unit. And let's go on to our next page. Okay, so these are already filled in for you. But I am going to probably do a little bit of extra writing as we go in. And remember, these are also posted to Google Classroom. Okay, so for kinetics and equilibrium, the big overlying concept is what we call collision theory. And it basically just sounds like it is. In order for a reaction to occur, reactant particles must collide, right? If they don't hit each other, right, they don't come into contact. There has to be physical contact, right? And that contact is what we call a collision. And now, in order for a chemical reaction to occur, not just any contact will do. You have to have contact or collision with the proper amount of energy, right? And so this is going to be kinetic energy, right? And so that's the energy of motion. And we really want them to have a high kinetic energy of collision. And they have to have a proper orientation. That means it just basically has to line up just right. Like if they can't just ricochet off each other, right, they need to collide together in a certain spot. So just like with enzymes with lock and key, right, there's only certain areas of a molecule that are going to react. So you have to keep that in mind when designing an experiment. So only when particles collide with enough energy and orientation, right? So they have to have the correct amount of movement and they have to be lined up. Will there be what we call an effective collision, Not all collisions are effective, right? If it's effective, the chemical reaction occurs. So increasing collisions increases the reaction rate, right? So let's focus on the word rate. Right, so you might be a beginning driver, and if you're driving 65 miles per hour, that's a rate, right? That means in 65 minutes, you will drive 65 miles. 60 minutes, you will drive 60 miles, right? Miles per hour. So a rate is something that changes over time. Right? So you can have an interest rate, right? If we're talking about economics, right? So that's how much interest over time. So then in terms of reactions, it's change in concentration over time. And that's going to be concentration of product. So I'm just going to write prod because I ran out of space. Okay, so now what we need to figure out now is the factors that affect the rate of reaction. So that's going to be either increasing or decreasing the rate of reaction, because there's situations where we would want a reaction to go faster. There's other situations where we would want a reaction to slow down. So the first factor is the nature of the reactants, and that means what type of bonds are present in the reactant particles. So if you have ionic bonds, are going to be faster. Remember, ionic is a metal and a nonmetal. And covalent bonds are going to be much slower. And organic molecules are going to be the slowest because they have lots of bonds to break. So ionic, right? Here we have a metal and a nonmetal, right? Just throwing in a little review. And here I have a metal and a polyatomic ion. So I have two ionic compounds. So then this one is going to be the fastest. If I'm comparing that to this reaction, even though this is a combustion, this one will be faster because the bonds are easier to separate. All right, so the nature of reactants. So the next factor that influences or can change the rate of reaction is concentration. So remember, concentration right, is going to be most of the time molarity, right, which is moles over liters, or parts per million, or a percentage. So if you increase the concentration, right, then you're going to increase the reaction rate. And then whenever you're increasing a reaction rate, the reason why it's increasing is because there are more collisions. So the more particles you have present, right, the more moles per liter, the more collisions there are going to be, right? They're going to hit each other more. The more you pack into there, the more likely they are to hit each other when they're flying around. It's going to be a faster rate. And then the reverse is also true, right? If I decrease concentration, I'm going to decrease the reaction rate. Now, pressure. Pressure only exists as a factor in the reaction rate if you have gases present. Because remember, we had a whole unit that related to gases, because gases are compressible. So then pressure is only going to affect the physical properties of a gas. If I increase the pressure, I'm going to increase the reaction rate because I'm pushing those particles closer together. If they're closer together, they are more likely to collide, the collisions, right? An increase in pressure decreases the volume, right? So our pressure, temperature, volume, if I increase the pressure, then the volume is going to decrease. That's an inverse relationship, right? If I increase the pressure, they decrease the volume. So less space means they're going to hit each other more frequently. So that's going to be an increase in collisions, an increase in reaction rate. And of course, now the reverse is also true. If I decrease the pressure, right, so stop adding pressure to the gas is going to expand, the particles go further apart, less collisions because they're farther away from each other, reaction rate will be less. And so now let's go into our temperature. Temperature is the one factor that's going to have the biggest influence on reaction rate, because what do the two things that a reaction needed for an effective collision? You need to have a high kinetic energy, right? Because temperature, again, is average kinetic energy. An increase in temperature increases the kinetic energy. The particles move faster. If the particles are moving faster, there's going to be an increase in the collisions that happen between the particles. And it's also increasing the energy of those collisions, right? They're going to hit each other with more force. So we're going to have an increase in the reaction rate. And again, the reverse is also true. If I decrease the temperature, I'm going to decrease the rate of reaction, right? If I increase the temperature, it's going to happen faster. If I decrease the temperature, it's going to go slower. And our last factor that can influence the rate of a chemical reaction, right, the collision theory, how particles are going to collide, is surface area. If I increase the surface area by making pieces smaller, I'm going to increase the rate. Again, because it increases the possible number of collisions. So if I have this big block here, and I compare that to all of these little itty bitty blocks, this one is going to be the fastest because it has the most surface area contact with the other particles, right? This one is going to be the slowest, right? Because when anything is going to try to react, it can only react out here on those surface. But with this one over here, all of those little blocks, everything can get all the way inside and it can reach all those other particles. So that one's going to react the fastest. All right, let's go on to our next page. Oops, I said that one was the last one, but it is not. I digressed. Our last factor that can influence the rate of a chemical reaction is a catalyst. So a catalyst you learned in living environment, right? So enzymes are catalysts. Enzymes make reactions happen, but not all reactions need a catalyst. So a catalyst is not something that is required, but it can be used to speed up a reaction. So I can have this reaction that's going kind of a little bit slow, and I'm like, I'm a little impatient. I want to speed things up a little bit. So if I want to speed things up a little bit, I'm going to add a catalyst. A catalyst will speed up a reaction and it doesn't get used up. It doesn't take part. It's not a reactant. And don't forget, the reverse is always true. If I take the catalyst out, I will slow down a reaction. Maybe the reaction is going a little too fast for my liking. I want to take the catalyst out. It's going to slow it down. But how does it do that? Again, it's always about the collisions. So what happens with a catalyst is it provides an alternate reaction pathway, and it lowers something called the activation energy. So what that means is, what is an alternate reaction pathway? If I told you that you were going to go from my classroom to the gym, and I wanted you to find an alternate pathway to get there, that's a shortcut. That is basically a catalyst. If you can find a shortcut, let's just call that a shortcut. Catalyst is a shortcut. It's an alternate reaction pathway. So speaking of pathways, and speaking of this thing called activation energy, the word activate means to start. So if I have the activation energy, that's going to be the energy to start a chemical reaction. And that's going to be one of your vocabulary words. With chemical reactions, we have a new way of drawing what happens in a chemical reaction. And that's what we call a potential energy diagram. So this is basically the pathway for a chemical reaction. And it's going to talk about the potential energy. Remember, potential energy is the stored energy. So that's the energy stored in chemical bonds. So recall from when we talked about bonds, when bonds form, energy is released, and when bonds break, energy is absorbed. So we have release and absorb. So that means we have two different types of diagrams. We have a release diagram and we have a absorb diagram. So we have an endothermic and an exothermic. So this shape graph over here on the left, this shape here is a exothermic shape. Notice I know it's exothermic based on where do we start, right? So this is where we start, and then this is where we end, right? So whatever you start with in a chemical reaction is the reactants, and whatever you end in a chemical reaction is the products. So if the products end up being lower, you have an exothermic reaction. That means it releases heat. And then heat will appear on the product side of a chemical equation, right? We've seen that before when we talked about chemical equations in our chemical equations unit. If heat is a product, it's indicating an exothermic, right? It means heat is released. If I start off with 40 kilojoules of potential energy, but I end at 20, what happened to the heat? The heat was released, exothermic. So if I start over here, and let's put numbers over here. So let's say this is 30, and let's just say that's an 80. Just making up numbers. So this is an endothermic, and so this means this absorbs heat. So if my ending line is higher than my starting line, that means it's endothermic. That means it had to take in energy, right? Potential energy. This is an energy diagram. So if I start at 30 and I end at 80, that energy had to come from somewhere, so it had to absorb that energy. And so we talk about the absorption or endothermic. Heat is on what we call the reactant side, right? Remember, reactants are on the left and products are on the right. I said earlier we had this thing called activation energy. That's the energy to get a chemical reaction started. So to get a chemical reaction started, I got to get up here. This is where the chemical reaction starts. And this is something called an activated complex. At the top of this hill is something called an activated complex. It's kind of like this thing that has to kind of go, it's like an intermediate. And then it's not a reactant, it's not a product. Things are just starting to rearrange themselves. And that's where the reaction is just starting. because you got to have some energy, right? Everything needs some form of energy to start off with. And so right up here is the activated complex on this other graph, right? The top of the hill. So if I need to get to that activated complex, I need to get this reaction started, I have to go from here to here. I need that much energy to get this thing started. And over here, I need this much energy to get this thing started. So then what is that energy to get things started? That's what we call the activation energy. So activation energy. I'm going to line that up, activation. Oops. I'm just going to do active energy for the sake of space. Active. Ooh, terrible writing. Let me erase that. Okay. So activation energy. Okay. So that's the amount of energy. So I've got numbers over here on the side. If I start off at 40 and to get to 100 to get this reaction started, how much energy did I absorb? So from 40 to 100, the activation energy in this case is going to be 60 kilojoules. And if I start off at 30 here, and then let's say that this is 100 up here, then this is from 30 to 100. So what is that? The activation energy would be 70 kilojoules. So which one takes less energy? This one. This one only took 60 kilojoules of energy to get started. This one took more. Okay? So even though this is exothermic and it's a release of heat, you still have to get some energy in it to start it going. But overall, this is how much energy is released. So this is basically your digestive process, right? So in living environment, when they talk about when you break a bond, energy is released. So then in chemistry, I tell you that when you break a bond, energy is absorbed. So then both are true, but you have to absorb energy to break the bonds, right? This is that activated complex, right? You've broken the bonds. Now those bonds are forming, but right, we form new bonds here to make the product. And then overall, the product ends up lower, so there's some energy released in that formation of the new product. That's what happens in this whole digestive ATP process. You do have to add some activation energy in first. Energy has to be absorbed first, but overall energy can be released. And in some cases, you really need to overcome some energy. So you need a much larger activation energy, but overall, you're not releasing in an endothermic. Overall, you still need to have, add more energy. So then that's where you end up with a endothermic reaction. All right, so that is going to be it for this set of notes. And there should be some practice problems associated with that along through the video. And then our next set of notes, we're going to continue with this graph because these graphs are very important for the whole rest of the unit. We're going to be using them to diagram the whole rest of the unit. So make sure that you understand, maybe go back and review what I've talked about in this graph.